This is a video from section 4.1 in a linear algebra class. Let A equal the set that contains the numbers 1, 2, and 3. Let B equal the set that contains nothing in it. B is called the empty set because it doesn't have anything that's in the set. A is an example of a non-empty set. In example 1, let W equal the set of all 2 by 2 matrices of the form A0, 0B with standard matrix addition and scalar multiplication. Now, one thing I want you to notice about this particular 2 by 2 matrix, notice that the entries along the main diagonal are real numbers. A and B are real numbers. The entries off the main diagonal are always 0. Okay? Now, is W a non-empty set? The answer is yes. How do I show that W is non-empty? I want to show that W has the 0 matrix. Now, it does turn out that the matrix in which each of the entries are zeros, right? And that's a 2 by 2 matrix, by the way. This matrix does belong to W. Since the entries along the main diagonal are real numbers, right? 0 is a real number. And the entries off the main diagonal are 0. So notice how it takes on this form. And so therefore W is indeed non-empty. Part B. Is W closed under addition? The answer is yes. How do we show this? Now, we're going to pick 2 matrices in W. And we're going to show that when we add them up, that sum also belongs to W. So we're going to let the matrix A100B1 and the matrix A200B2 belong to W. We want to show that the matrix A100B1 plus the matrix A200B2 also belongs to W. So let's start there. Now we're going to take the matrix A100B1 and we're going to add the matrix A200B2. By matrix addition, and this is probably the most important step to this proof, this is equal to the matrix A1 plus A2, 0 plus 0, 0 plus 0, B1 plus B2. So again, this is matrix addition. Now, this is equal to the matrix A1 plus A2, 0, 0, B1 plus B2. Now, this matrix written here belongs to W. Why? It's because the entries along the main diagonal are real numbers and the entries off the main diagonal are 0. So notice A1 plus A2 and B1 plus B2 are real numbers. And then those are the entries along the main diagonal. The entries off the main diagonal are zeros. And so therefore, the matrix A100B1 plus the matrix A200B2 belongs to W, and we can say W is closed under addition. Part C. Is W closed under scalar multiplication? The answer to this question is also yes. Let the matrix A00B belong to W and let K be a scalar. We want to show that K times the matrix A00B belongs to W. Now, start with K times the matrix A00B. But this is the matrix KA, K times 0, K times 0, KB. And this is the matrix KA. And remember, K times 0 is 0. So it's KA0, 0, KB. And I want you to notice something. Notice that the entries along the main diagonal are real numbers. The entries off the main diagonal are 0. So this matrix absolutely belongs to W. Right? And if this matrix belongs to W and this matrix is equal to K times the matrix A0, 0B, then K times the matrix A0, 0B also belongs to W. And W is closed under scalar multiplication. And that's what I wanted to go over in example 1. I wanted to show you closed under addition, closed under scalar multiplication, and how do you show that a set is non-empty. So we're going to do the same thing for example 2. Let W equal the set of all 2 by 2 matrices A for which the determinant of A is 0. Part A, is W non-empty? Yes. Why? Because if we set B equal to the 0 matrix, right, and that's the matrix in which all the entries are 0, and notice that B is 2 by 2. So B is a 2 by 2 matrix, and the determinant of B is indeed 0. And so that tells me that B belongs to W, and that shows W is non-empty. So notice, just like in example 1, we showed that W contains the 0 matrix to show that W is non-empty. It's really important. Part B, is W closed under addition? Interestingly, the answer is no. Okay? Now, we can use a specific example to show why it didn't work. And that's exactly what we do here. Let A equal the matrix 1, 2, 1, 2, and let B equal the matrix 1, 1, 2, 2. A and B belong to W since A and B are 2 by 2 matrices, and the determinant of A equals the determinant of B equals 0. So A and B are absolutely in W. But if I take A plus B, it turns out that this is equal to the matrix 2, 3, 3, 4. Now, A plus B is a 2 by 2 matrix, absolutely. However, the determinant of A plus B doesn't equal 0, and therefore A plus B cannot be in W. It doesn't belong to W. And therefore W is not closed under addition. So when you want to show something's not true, a counterexample is sufficient. But if you want to show something is true, you have to do it in general. Very important. Part C, is W closed under scalar multiplication? The answer is yes. Now, let A belong to W and let K be a scalar. A is a 2 by 2 matrix, and the determinant of A is 0. Now, a scalar multiple of a 2 by 2 matrix does not change the size of the matrix. It doesn't change the dimension. So it turns out that Ka is also a 2 by 2 matrix. And if I take the determinant of Ka, this is equal to K squared times the determinant of A. That's the properties of determinants. And this is equal to K squared times 0, right? Remember, A still belongs to W, so we do know the determinant of A is 0. So K squared times the determinant of A is equal to K squared times 0 equals 0. So Ka belongs to W, and we have thus shown W is closed under scalar multiplication. So again, we showed W is not empty. In this example, interestingly, W is not closed under addition, but it is closed under scalar multiplication. Example 3. This one's a good one too. Let let W equal the set of all 2 by 2 matrices such that A times the column vector 1, negative 1 is equal to the column vector 0, 0. Part A, is W non-empty? Yes. Why? Now, the 0 matrix is a 2 by 2 matrix, and If I take that 0 matrix and multiply by the column vector 1, negative 1, I absolutely get the column vector 0, 0. And so this 0 matrix belongs to W, and we can thus say W is non-empty. So that's part A. Part B. Is W closed under addition? Yes. Let A and B belong to W. We want to show that when we add A and B up, that sum belongs to W. So in other words, I'm going to let A and B belong to W. I want to show A plus B belongs to W. Since A and B belong to W, A and B are 2 by 2 matrices, and if I take A and multiply by the column vector 1, negative 1, I get the column vector 0, 0. And if I take B times the column vector 1, negative 1, I also get the column vector 0, 0. Now, adding two matrices of the same size or same dimension does not change the dimension of the matrix. And so what that tells me is A plus B is a 2 by 2 matrix. Now, let's look at the second half of this. If I take A plus B and I multiply by the column vector 1, negative 1, remember these are matrix properties. We can say that this is equal to A times the column vector 1, negative 1, plus B times the column vector 1, negative 1. But this is equal to the column vector 0, 0, plus the column vector 0, 0, since A and B belong to W. But this is equal to the column vector 0, 0. And so therefore, A plus B belongs to W, and therefore W is closed under addition. Part C. Is W closed under scalar multiplication? Absolutely. Let A belong to W and let K be a scalar. We want to show that Ka belongs to W. A scalar multiple of a 2 by 2 matrix is a 2 by 2 matrix. And so we can say that Ka is a 2 by 2 matrix. Now, if I take Ka times the column vector 1, negative 1, I can pull that K out in front and multiply by A times the column vector 1, negative 1. So a theorem allows us to do that. Okay? And remember, A times the column vector 1, negative 1 is the column vector 0, 0. And so here, remember, A belongs to W. So we can write this as K times the column vector 0, 0. But this is equal to the column vector 0, 0. And so we can say that Ka belongs to W, and we can thus conclude W is closed under scalar multiplication. Now, let me kind of give you an idea here. Suppose I let V equal the set of all first degree polynomials. So, in other words, it's of the form A plus BX, where A and B are real numbers. Okay. Is V non-empty? Now, does it have 0? It's the nicest way to show non-empty. So remember, 0 is equal to 0 plus 0x, right? Notice how this side takes on this form, right? So can we agree that 0 plus 0x belongs to V. And so we can say that 0 belongs to V. And so V is non-empty. That's the idea there, right? Like if I wanted to show, suppose I want to show V is closed under addition. Now, we're used to adding first-degree polynomials, right? See, if I let a1 plus b1x and a2 plus b2x belong to V, I want to show that if I add these guys up, so in other words, if I take a1 plus b1x and I add a2 plus b2x, when I add them, I want that sum to belong to V. Right now, that's not immediate. Why is that not immediate? Because it doesn't look like this yet. To be in V, it has to look like the form a plus bx. It has to. Now look, if I take a1 plus b1x and I add a2 plus b2x, okay? Absolutely, we can write this as a1 plus a2, right? Rearranging the terms, plus b1x plus b2x, for sure. Now, does this look like this form? The answer is no. Okay, not yet. One final step is we have to write it this way. If I factor out that x, I get b1 plus b2 multiplied by x. So in other words, I get a1 plus a2 plus the quantity b1 plus b2 times x. This absolutely belongs to V, right? Remember, a1 plus a2 and b1 plus b2 are real numbers. Okay? And that's the idea there. Now, if we wanted to go over scalar multiplication, I would say let a plus bx belong to V and k be a scalar. So we want to show k times a plus bx belongs to V. In its present state, it doesn't at all, okay? So in other words, what we need to do is look at k times a plus bx. But this is ka plus k times bx. But this is ka plus, using the associative property, kb times x. And in this form, that does belong to V, for sure, right? Because Ka and Kb are real numbers. And it takes on, where'd it go? It takes on this form. And so that implies K times A plus Bx belongs to V, and V is closed under scalar multiplication. And I hope we get an opportunity to check out this video prior to Monday. Okay, that'll do it for this video. For section 4.1, we looked at 3 specific properties showing that a set is non-empty, closed under addition, closed under scalar multiplication. Okay, thank you.